Hi,
Good to see you.
good to see you, Nicola.
Well, can you hear me well?
Yes, yes, we can hear. Excellent.
Excellent. Where are you at the moment?
Actually, in my office,
Ah, right. And this is in Bonn, right?
that's in Bonn, at the DZNE, German Center for Neurodegenerative Disease.
Excellent. I'm in Macedonia, in Skopje.
Oh, okay, nice.
And I think last time I spoke to Philip, he was at the Max Planck, right?
Yes, I was at the Network Plank in Tübingen, exactly.
Yeah. How long ago was that? Was that like 2 years ago with Klaus Scheffler?
2.5 years, probably, yeah.
Wow, it's been a while. Yeah, you were one of the first highlights interviews we did, I believe.
Oh, really?
So yeah, good to see you again. And Tony, I believe it's the first time for you, right?
It is, yes.
Wonderful. So usually we start with just some brief background questions, in particular how you got into MRI.
Mhm.
And I guess we've heard a little bit about Philip's story, but maybe he can say it now on video as well.
Yeah, so I basically studied physics in Würzburg, and of course, at the time there was a big MR group. There's still a big MR group there, and so I basically got sucked into this group. First of all, I started with NMR during my diploma thesis, and then during my PhD, I worked a lot of on relaxometry. Yeah, exactly. And then after Würzburg and a brief visit in Cleveland, I went to Tübingen, so where we then had an interview about the previous topic, so balances FB functional imaging, which was my main topic in Tübingen.
Well, you're becoming a highlights regular now, so good to see you on a different topic.
Yeah.
And Tony, how about you?
Well, I studied at the University of Bochum. I actually studied geophysics and did also my PhD in geophysics, so in seismic tomography, on tomography on larger scale, and just entered the field of MRI afterwards, which is some time ago, and started in functional imaging I think, in the year 2000 at the clinics in Düsseldorf, and afterwards worked with John Shah at the Research Center Jülich for quite some time, before I then had the opportunity to have my own MR physics research group here at the DZNE in Bonn.
How long have you been in Bonn leading your group?
So the DZNE is a rather young institute, which started only in 2009, and I joined the DZNE in 2012. And we got the scanners in 2013. So first year was hard, but now it's good.
Wonderful. So are you ready for the audio slides?
Yes, yes.
Hello, my name is Philipp Ehses, and I will present a brief summary of our paper, Whole Brain B1 Mapping Using Three-Dimensional Dream, with my co-authors Daniel Brenner, Rüdiger Stirnberg, Eberhard Bracht, and Toni Stöcker. Flip angle or B1 plus mapping is important for many applications, such as quantitative MRI, where you often need a flip angle in order to obtain accurate perimeter maps, such as T1 or T2 relaxation times, or multi-channel transmit applications, where we require knowledge of the B1 field of individual transmit channels for B1 shimming or to calculate product-transmit pulses. And is particularly important at ultra-high field due to large B1 variations, which again makes it necessary to know the flip angle in order to either correct for variations retrospectively or to apply multi-channel transmit techniques during the scan in order to mitigate them. However, flip angle mapping often requires long scan times, especially if a large 3D volume needs to be covered, and even more so for multi-channel mapping. So, the goal of this work is to develop a fast 3D flip angle mapping technique that can serve as a quick calibration scan and can be included in all our study protocols, and additionally that allows for multi-channel mapping in a reasonable amount of time. We chose the dream sequence as a starting point, which consists of an initial steam preparation followed by a quasi-simultaneous acquisition of the free induction decay and steam signal within a single gradient echo readout train. The flip angle of the preparation pulses can then directly be obtained from the ratio of the steam and the FID signal. We implemented a 3D version of the technique with a non-selective RF excitation and a center-out view ordering, as illustrated here on the right. Note that acquiring a 3D volume requires a pretty long readout of a few seconds, although a multi-shot approach with a shorter readout train is also possible, at the cost of a longer overall scan time. This illustration again shows how the flip angle is calculated from the ratio of the STEAM and FID signal. As you can see, due to the long readout, the STEAM image shows quite a bit of blurring, whereas the FID image remains relatively sharp. These blurring differences in the two images translate into ring-like artifacts around the brain and prominent ventricles in the flip angle map. To understand the origin of the different amount of blurring, it is helpful to take a look at the signal evolution during the long readout. The FID signal evolves from its initial value towards the FID, or flash steady state, which, depending on the excitation flip angle beta, can be higher or lower than its initial value. In contrast, the prepared STEAM signal simply decays to zero, with the same flip angle dependent relaxation rate as the FID signal. Thus, at the end of the readout, which corresponds to the outer part of K-space, there is very little signal left, which explains the strong blurring in the STEAM image. If we now look at the apparent relaxation rate, we can see that even for flip angles as low as 6 degrees, the signal decay from saturation, due to the repeated application of excitation pulses, outweighs that from T1 relaxation. If we now choose a large beta, we gain the advantage of a high initial signal. However, from the apparent relaxation rate shown here on the bottom left, we can see that the signal decay for larger flip angles is very strong. This is, as we have seen, problematic, especially for long readouts. But since the apparent relaxation rate is dominated by saturation, the signal decay is almost independent from T1. So, is it possible to use this knowledge about the signal evolution in order to correct for this effect? We know where each K-space position is sampled, and we can get a flip angle estimate from the DREAM experiment itself. In addition, T1 is not super important, so a rough guess, for example for gray matter T1, should be good enough. With this knowledge, we can get a good estimate of the FID and STEAM signal evolution inside each voxel. The idea is now to let the blurring in the STEAM image determine the blurring in the flip angle map. We can achieve this by artificially blurring the FID image according to the known signal evolution, so that it resembles the amount of blurring in the STEAM image. Here is a comparison of the STEAM and the FID image before and after applying the filter for unaccelerated as well as parallel imaging accelerated data. As we can see, blurring in the filtered FID image resembles blurring in the STEAM image now. Additionally, parallel imaging helps to reduce overall blurring, which is expected since it significantly reduces the duration of the readout train, in this case by a factor of 4. This figure illustrates simulation results from an artificial phantom with spin density and sinusoidal-shaped flip angle scale distribution, as shown on the top left. As we can see from the difference to the known truth, the conventional DREAM reconstruction shows pronounced edges, which are improved by both tested filtering strategies. In case of the global filter, a single filter kernel is determined from a global flip angle estimate and applied to the whole 3D volume. In contrast, the local iterative approach uses a voxel-dependent filter kernel based on the initial DREAM flip angle map. As you can see, the local iterative approach provides best results, with a mean average percentage error below 1% after only a few iterations. This slide shows the in-vivo results from single-channel mapping experiments. Especially in the unaccelerated data, but also in the 4x accelerated data, the ring-like artifacts around the brain, indicated here by white arrows, are clearly visible, and other tissue boundaries such as the ventricles also appear very prominent. The blurring compensated reconstruction reduces the amount of artifacts and compares very well to the multi-shot DREAM as well as a Bloch-Ziegert shift reference experiment. And here are the results from a multi-channel mapping experiment. The 8-channel whole brain DREAM maps were acquired in a scan time of only slightly over 1 minute and are again very similar to a Bloch-Ziegert shift reference experiment, shown here at the bottom. To conclude, we present a 3D implementation of the DREAM sequence which requires a long readout train compared to the two-dimensional case. As a result of the long readout, the different STEAM and FID signal evolution causes problems, especially close to tissue boundaries. In general, shortening the readout helps here, which can either be achieved by introducing multi-shot segmentation, which takes scan time, or parallel imaging, which leads to noise enhancement, especially at high acceleration factors. We propose to alternatively or additionally compensate for these blurring differences by artificially blurring the FID image according to the expected blurring in the STEAM image. With this, the proposed 3D DREAM implementation allows for single-channel whole-head mapping in only a few seconds and for 8-channel whole-head mapping in approximately 1 minute. Thank you very much for your attention.
We are back here with Philipp Ehses and Toni Stöcker from Bonn, and we'll have a chance to discuss with them a little bit about the 3-DREAM sequence that they developed. This work is a follow-up of the original DREAM sequence that came from Nerke and Bernert, 2012, I believe. And you managed to make it 3D and you managed to make it fast.
Yes.
So Philipp, maybe you can tell us about the path from that 2012 paper to the 3-DREAM today.
Yeah. Okay. So actually, at the beginning, I wasn't even here yet. So this, so the main idea is from a predecessor, from Daniel Brenner. So he started with the 3D sequence.
Yeah, there was a small abstract in Milan, I believe, right? Like 2014, 2015.
Yeah, exactly. So, and it was then just to jump in here because I think Philipp was not involved at that time. Originally the idea was, we spent a lot of time on 3D readouts and especially on 2D phase encoding readouts, center out readouts, all Cartesian, and also, and at some point Daniel Brenner had the idea, well, that's because he was also doing a lot actual flip angle imaging and testing that versus Bloch-Siegert and so on and so forth. And then this DREAM paper came out, and we thought, well, that's really a very fast and cool technique. And because we were working on all these 3D readouts, we thought, well, let's try to apply that and try to do that with DREAM. And that was then the result was that ISMM abstract in Milan, yes. And well, from the first idea to have really then a well-working technique was quite some way. And in that way, Philipp was also very much involved.
So Philipp, how long were you working on this? Was it since you came to Bonn?
Basically, yes. Yeah, exactly. So of course there were other projects as well, which also some stuff I had to finish still from Tübingen. But yeah, this was then my main scientific topic after I came here.
So it seems that the biggest challenge you're facing here is this blurring that you observe, and trying to compensate for it required some additional blurring. And maybe the first question I have is, rather than try to go for an average T1 value and then try to estimate what the blur might be and try to compensate that way, what if you just try to blur at the end when you have this sharp image with the ring and the CSF? Do you think that might also work as a somewhat simpler approach?
I don't know. I mean, you mean, yeah, so the problem is blurring afterwards may work, but in the end, I mean, the reason for the artifacts is basically because the blurring is different between the two images. So of course you could basically apply the filter in the end somehow, but then it's probably more complicated. Depending on how much blurring you will add, it may work, but I think it's the better way is to use the signal equation. And then
no, absolutely. I mean, this is, here there is actually a physical reason for doing the blurring, and that's important. I think very often people do the blurring and they don't report it, or there isn't a very systematic way. So we know that there shouldn't be too much structure, so let's apply a spline or let's apply a Gaussian, and there you go. We don't observe any of the rings and any of the ventricles. So Toni, any thoughts on the choice of the blurring parameters and how that came about?
I mean, the choice is pretty simple right now. So basically, the blurring is determined by the flip angle, by TR and by T1. So, and of course, the length of the echo train. So for faster readouts, the blurring is less severe. So we don't need to add so much blurring to the FID image. And so the flip angle we get from the experiment itself, and we iteratively improve the flip angle estimate. And T1 we just have to guess. I mean, TR of course is known, but T1 we have to guess. There's no way around this if we don't want to do time-intensive T1 mapping. And so the simplest way here was just to use basically an average T1, and then the difference from this average T1 is not so big in the brain, except maybe for CSF.
For the ventricles, right? Yeah.
Exactly. Yeah. So this is the best choice, best estimate we can just quickly do.
And as we have shown in the paper, I think we have is that if T1 estimate is not very accurate, the influence on the flip angle is not actually very strong. So
yeah, it was just 1 or 2%.
Yeah.
Now, the other interesting thing here is that you actually spent a lot of time making the code available, and you actually have a beautiful Jupyter notebook that I actually found on GitLab.
Yeah.
Where did the motivation for that come from, and what do you hope to achieve by making your code available?
Yeah, I mean, motivation is I profited a lot from other people making code available, and I think it's always a good idea to do so. And it will also, of course, maybe help to generate interest for the technique. So I think it's just there are lots of benefits for both sides, basically, for the scientists who did the work, and also for other scientists who maybe want to reproduce the work. Yeah.
And Tony, is this a practice for your lab? Do you try to make the code available and publish most of it as a Jupyter Notebook?
Yes, absolutely. Jupyter Notebooks, C++, whatever. Or GitHub on publishing code on GitHub. So we try to do that if possible. Sometimes, for example, with this sequences on the Siemens scanner, it's not so easy. But if possible, I'm very much supporting sharing code. I think it's very, very important aspect to move on, and to being able to reproduce research by others and making available done, so that makes the whole thing much easier and faster, and that is what we would like to support.
And what about the pulse sequence? How easy is it to implement it, and how easy would it be to port to another site?
Well, I mean, yeah, that depends, I think, very much on the platform, how easy it will be to implement. We can only speak for Siemens. I think, implementing it from scratch would be a lot of work. Surely, sharing code is not that trivial, but we do share it via the sequence binaries via C2P, and we did that with many other institutes already. So that's basically how it is.
So by your estimate, how many centers are running this sequence at the moment?
I think we counted it recently, so it was 18, I think.
Yeah,
that's very impressive. And do you think it might be becoming a stock sequence at some point, or you're still in the C2P state?
Yeah, we're still in the C2P state, so everything else is we don't know yet.
Out of your control.
Exactly.
It's really nice to see reproducible research promoted in highlights, and we hope that people will actually consult your code and maybe decide to implement 3Dream. Mm-hmm. Maybe you can give us some parting thoughts. What challenges do you foresee going forward, and what would you like to do with 3Dream in your center, or maybe broader on the Siemens platform?
Yeah, I mean, for us, of course, we now want to apply the technique. So it's very important for us already. So we already have quite a few studies basically where we require B1 mapping. or we just want to know about the V1 field. So sometimes it's just, I mean, sometimes something goes wrong, so it's always useful. So if you have a quick 5-second scan in every study protocol, then that's very helpful, for these studies. And in addition, of course, we want to go to paratransmit and V1 trimming, and in this case, it's also very useful to have a quick way to run a V1 scan for all 8 channels in a minute or so, maybe. So.
And Tony, what kind of applications are you considering? Is it basic T1 mapping or something a little more involved on the quantitative MRI side?
Well, I mean, I think for many quantitative MRI applications, knowledge of the flip angle is required. So if we want to be quantitative, we need to know the flip angle. And in that sense, I think it's really a very general tool, applies in many situations. And as Philipp just said, if it just takes a few seconds to acquire it, that can be basically applied in many different situations. And that's exactly what we do, and also what we suggest then to users who come to want to set up new studies. We try to convince them that it's useful to do that, even if they don't know at that point exactly why they probably would need the flip angle. But if it's just a few seconds, it can help then later on, for example, in, I don't know, different approaches for quantitative MRI, multi-parametric mapping or standard T1 mapping. In many ways, the 3DREAM could help, and that's that's one thing. And as Philipp said, for pulse design, for paratransmit, it is definitely also required, but this is something where we just actually are now starting to use it and get more knowledge about it.
Wonderful. Thank you. So I guess it's Tuesday afternoon for both of us. We're in the same time zone. What does the rest of the day look like for both of you? Philipp, what will you do after this interview?
Actually, we'll do some file sequence programming again. So I'm working currently on a spiral sequence, actually. So yeah, that's the rest of my day. So pretty fun day today for me.
Anything for after work? How's Bonn after hours scene?
Okay, that was the question. Yeah, so
both actually.
I mean, usually what I do Tuesdays is actually I'm going rowing on the Rhine River, but today it's pretty bad weather, and also it's getting dark very early now. So yeah, so I will leave this for the weekend then.
And how about you, Tony?
Well, yeah, for me, the rest of the week will be the ESMRMB in Rotterdam, where I'm going there tomorrow afternoon, and I'll start doing some preparations for the meeting, and then also actually next week, from next week, the semester starts here at Bonn University, so I have to also start thinking a bit about my lecture next week. So I'll be busy until the evening.
Wonderful. So it was good to see you both. Thank you for taking the time. And we look forward to hearing more about the applications of 3DREAM.
Yeah, thank you very much.
Thank you very much.